Hello. Today we're going to work through the solution to the coding part of this first homework, or I guess this is the second homework. Right down here. We're just going to compute gravity gradient tensor over a rectangular prism and map the components in units of Etvosh. I'm not really sure if this is in the CGS system. I think it is, but I would remain skeptical. 'Cause I think it might be even unitless. We can check. Oh no, this is CGS. Gal per centimeter. I thought it might have been a type of dimensionless parameter, but I was wrong. We'll need that page later, so I'll just leave it up. Yeah, I figure we'll just get right into coding these things up. No sense in delaying the inevitable. So I'm going to go like this. Did I do that wrong? Whatever. Okay. Sorry. We're back to running. I saw that most of you code in Python, so that's what I'm going to code this solution up in. If any of you would prefer C, I can re-record this, but I don't think y'all want to listen to me for that long. So we'll just start with Python and work from there. First things first, I just want to get these constants correct. I'm going to take the value in the SI unit system because I just want to be consistent. Consistent, start. Rho is, let's just set it to 0.3 grams per cubic centimeter. This is the SI unit system, and this is the CGS unit system. Back to the actual problem. So to compute the diagonal terms of the tensor, we need to evaluate this arctangent function. I think the arctangent in Python is in math. I think it's called arctan2. Yeah. Let's go. We'll need arc. Oh no, it's called atan2. Is it? I already forgot what I just saw. It's atan2. What is log called in this language? Oh, it's just called log. Okay. Yeah, I need atan, I need log, and those are like the only two like crazy functions we need. Everything else is gonna be pretty simple. Diagonal. Or let's just call this like XX. I don't know. Def partial. We'll have a function like this, and we need the difference in the y coordinates. We need difference in the z coordinates, difference in x coordinates, and a total distance r. Oh, I guess we need the square root too. And that's the dx. Yeah, Python doesn't do the whole exponential with the caret sign. I think this caret sign is reserved for the XOR operator in this language. But you know, this double thing, that's all right. I'm not gonna complain too much about it. And this is y minus y prime z prime x minus x prime. We're gonna need all these as inputs. How does this look again? Atan 2, and this is the numerator over the denominator. Atan 2 takes 2 arguments because it does not throw away the phase like the normal arctangent function would. Maybe that's not obvious. Let's go. Yeah, we can just go look up what arctangent of 2 is doing. So in the regular arctangent, you take a ratio of y over x. When you take a ratio, signs cancel. You know, if you divide a negative by a negative, you get a positive. But a negative, so that what that cancellation does is it gives you a 180-degree symmetry around the origin of the unit circle. This point xy here is the same as the point x, well, it'd be, yeah, xy down here. What arctangent 2 does is it records the sign so you get 360 degrees of function output from pi to negative pi around the circle, rather than just this internal line, which would be the result of taking arctangent. So arctangent only is this middle line, but arctangent 2 also includes these top lines for different arguments y over x, depending on the sign of x. Okay, maybe that's too obvious, but you know, sometimes people don't know the difference between arctangent 2 and arctangent, so I think it's just good at least to repeat that stuff. I already made a typo. Okay, but anyway, here's the partial of x. And I guess I should multiply by these constants since we're here. Or maybe these should be arguments to a function. Now, the partial of x needs to be evaluated at A2 and A1 for the x values, B2 and B1 for the y values, and C2 and C1 for the z values. So we can do that here. Let's call this just XX, I guess. And I guess we need all these terms too, huh? Okay. And what this notation means, oh, I prepared this slide down here in Paint. This notation here, you probably remember this from calculus class, but given any function, all this notation indicates is that you take this top argument, you plug it in for x, there's that first argument, and then you take this second argument and you plug it into the function, and then you subtract the two. Okay, so this notation is equivalent to this. So we're going to evaluate this 3 times, starting from the outside here and working inwards. So let's do, we can do partial, x, y, z. I don't know what x and y are yet, but we can do C2 minus x, y, z, don't know that, minus C1. Okay. And now we need to evaluate, we just did the outer one, now we need to unwrap the inner one. So this is where things start to get messy, but it's okay. We'll get through it. We can just start to put parentheses maybe around these. Partial xx, x, y, z. So inside each one of these parentheses, we're going to expand B1, B2, and B1. Right, and now in this bottom one, we're going to do the same thing. B2, B1. Okay, now again, oh god, this is horribly painful. We need to just expand the very last one of these things, the A2 minus the A1, for each one of them. Yeah, like this is the most painful part of this entire course. X, Y, Z. The good thing is it's really easy to see errors when you're done doing this, because there should be certain patterns in these indices once you're done. In your homework, actually, some of you took advantage of these patterns and did efficient evaluations, but I'm just going to do this, efficient evaluations of this expansion here with Levi-Civita tensors and all that complicated stuff, but I'm just going to do like the simplest possible way to do this. Just brute force it and plug everything in manually. So this isn't about being fancy, this is just about getting the job done. Just about getting the job done. There. I hope there's no typos. guys see any typos though, just scream at the screen and maybe I'll hear you. Z, last one. Whoop. Oh God. Okay. Do I have enough parentheses? I think so. Let's see. Oh, shit. I lost a parenthesis, sorry. Oh, I shouldn't use that language on recordings. Okay, I think we did this right. I sure hope so. Now we can check our indices too. Here we have 2 2 2 2 1 1 1 1. Here we have 2 2 1 1 2 2 1 1. Here we have 2 1 2 1 2 1 2 1. Okay, so that the indices are at least right. I might have messed up my parenthesis game, but they look symmetric to me, and so that's encouraging. You know, we see 2 1 2 1 parentheses, and here you see a pattern again. There's an extra parenthesis around this whole thing. Let's see. Is this really right? Yeah, I need one more parenthesis over here. Okay. Okay, let's hope that's right. So let's invent a test point. Again, I think we're allowed to use this kind of notation. A1 can be like B1, B2. Okay. I don't think this expression actually works inside the gravity prism, so it's important you place your test points outside the prism. Otherwise, it might look like junk. Or just be wrong. It might be right, though. I don't actually, I haven't read the papers on these formulas in a while, but you can find them in a, let's go look up a Sharma 1966. That's a famous paper too. This isn't the right paper either. But this is the source we're looking for. So let's just go like that. Click on the first thing because who cares? Boom. Yeah, this is it. So, Sharma's interested in computing magnetic anomalies and the demagnetization values for arbitrarily shaped objects. And what he starts with is little cubes, exactly the problem we're doing. Here's a Green's dyadic tensor. Maybe some of you recognize that from your earlier lectures. Oh, and here's those disgusting arctangents that we're evaluating now. But is this valid? The question is this valid inside the tensor? Maybe he says above. Pointing towards geography and downward. I don't see it. Oh. does he use this? Does he, because if he assumes a Laplacian field, then it must be outside the body. Only 5. Oh yeah, we did that in this assignment. The calculation of aforementioned setup. Rectangular prism involves no considerable difficulty. The divergence theorem, the volume integrals can be readily converted into surface integrals. The final expressions. So are we... I'm just trying to remember if we need to account for Laplace's equation, changing into Poisson's equation when we go inside these bodies. I wish he'd just tell me. Okay, we don't have time for this. Let's just solve the actual homework problem. This is what happens. Gotta be faster. B1, B2. The opposite ugly. Okay, let's do something like XX is... Sorry, I've been doing too much C lately. Temporary, invalid, decimal, literal. Oh, spelling. Where's that there? Line 20. My eyes cannot even see the... Okay. So it says it's 1. I have no idea whether that's reasonable or not. Let's just assume it is. Keep moving. I want to just like copy and paste this over and over and over. So maybe it would help to write like a helper function. Just call args. Yeah, let's just do it like this. Go back. Okay. And now we can do... I think we have to... I think this is like the correct way to do this. Okay, so... Now we've just taken our triple evaluation and moved it into a function. Valuation, if I can spell. A1, A2. Partials not defined. What the? Oh. Yes, this is why. Function. So what's the problem here? It takes 6 positional arguments, but 9 were given. Damn it. Yeah, there's this permutation. Okay, back to square one. I guess that's why you gotta be a little more careful. The problem was I was passing in 9 arguments here, but these only take 6 arguments each. So I technically need to pass in A2, B1, B2, C1, and C2. Okay, whatever, it's a little uglier, but I think that's the value we had before. This 1.23. Okay. Look, the reason I did that, moved that triple evaluation into a helper function, and technically we can do some real nasty stuff. I'm just going to define that function inside that function. Is that allowed? Oh, is it not allowed? Oh, correct indent one. Yes, so it's allowed. So each one of these partials is this inner integral. We just evaluate it 8 times because there's 3 of these expansions. We do that in the triple evaluation. I mean, this is kind of like unnecessary too. Let's just go like, yeah, like who cares if it's a little ugly? I don't. Now we can change this to YY really quickly. Just saying, hey, this should be X and this should be Y. Yeah, hopefully you can see that. And here's Z. This isn't like a course on programming style, so I would recommend you don't necessarily learn from me, but I don't like anything. Okay, so now we can have GDX is equal to XX. Let's just steal this line, right? Do all the derivatives of the diagonal. GDX. Y. That's sorry, I was trying to do some fancy Vim stuff. Sometimes it's just easier to do stuff manually. What have we got here? Oh, forgot to do this. Forgot to update the actual triple evaluation. Okay, and already you can kind of see that Laplace's equation is being satisfied at this point. So maybe we can just like drop an assert down here, and just to make sure that at all times Laplace's equation is valid, less than small number. small number is maybe like, I don't know how precise things should be. And this should definitely be an absolute value. Okay, so our assertion is passing. At least we've computed the gradient terms of 3 components at a single point. Now I guess we should do the triple evaluation at the off-diagonal points. X, Y. What does this one look like? Looks like this. Negative gamma rho. No, I'm not doing scaling yet, so let's just do this. No, I think log in Python is actually the natural log. But let's just make sure. I think it's math. Okay, math base E, it looks like, so we're good. And X and Y gets evaluated at DZ. Let's call that XY. Sweet. Let's go just copy and paste. Yeah, like don't tell your computer science teachers. This is how I code. Like I said, I just want to get the job done today. I want to get it done right. No debugging, please. See. Okay, I think that's right. Let me look for a second. Everything's still unscaled, but we're looking kind of good. Oh, I should have been a little more descriptive, huh? This isn't a scalar field name. This is a vector field. And I think I call that YZ, yeah. Let's do this now. Z RZ, yeah. X, Y, YZ, so see if this looks really abs. Oh, assertion failed because nothing is defined anymore. Okay, the assertion passes. You know, what the hell? Why are these the same as those? Is that supposed to happen like that? Oh, I must have not updated. Yeah, I didn't update these inner values. Z, Y, got. Yeah, maybe like more descriptive variable names would help. These 3 values are 0. Does that make sense? Does that make sense? I guess so. I think that makes sense because when we expand these three things, these are all logarithms. But these, when we're over a square rectangle right now. We're over a cube. We're over a cube. And we're right in the middle of it. So we have symmetry with respect to the xy plane. We have symmetry with respect to the yz plane. Although, I said that wrong. We have symmetry with respect to the yz plane and symmetry with respect to the xz plane. So I'd expect those to be 0. But that last one, should that really be 0? Somebody. Let's see. GZ dy. YZ. No, it shouldn't, because I typed in the wrong function name. Man. If we ever get through this assignment without an error, it's going to be a miracle. XZ. Am I going crazy? XZ, YZ, XY. Ugh, so many freaking letters. Let's just move forward and see if we're wrong at the end. That's how you're supposed to code, right? If it doesn't crash, we're probably all right. Okay, but now we have we've evaluated the full tensor now at each point, and we've confirmed Laplace's equation is satisfied, at least right there. So why don't we I don't know. Let's just end up, what I want to do is like evaluate this at multiple points. So let's try 800. All of our spatial stuff is in meters. And now we can go like for, I need a x cell size. What's in like a even number we can pick? I think 20 would be reasonable. In both. So for this step in the range x-min, so the number of actual points in this is going to be cell size. Because it's an even multiple, I think we can do the integer division. Oh, I did this backwards. Okay. So let's just see if I can even run this. You know, like, are we gonna crash? Oh, I need to find x. So x is equal to x-min plus dx times x cell size. It's weird that like Python won't even crash until you actually hit the point where you use an undefined variable. Like it's just happy letting undefined variables exist until you crash. Oh, that's a problem. jeez. Okay. I had put the wrong letter there, so that would have caused some major headache. We didn't crash though. We ran this assertion like a jillion times, so at least Laplace's equation holds everywhere. What else could we do? Yeah. I guess we're ready to export our stuff. Technically I should scale everything, shouldn't I? So that way and let's do like the same thing here. A row SI. I think 0.3 times like 1,000 will put us in SI. Okay. Let's think critically. SI would be kilograms per meter cubed. So grams to kilogram is multiplied by 1,000. Yeah. And centimeters to meters is a multiplication by 100. So what the total to go from grams per centimeters cubed to that, we need to multiply by 1,000 and then divide by 100 cubed. Is that right? Is that right? For some reason that seems like really wrong. Let's just move forward. Yeah. Just like usual. Just pretend like everything's gonna be alright. Yeah. We have Google at our disposal. Let's just not make a mistake. Grams per centimeter cubed to SI. Yeah, so somewhere I messed that up bad. Where did I mess up? Oh shoot, I probably shouldn't be on a site with ads during this recording. Maybe, what in the world did I do wrong? Oh, I think I need to... do it like this. Yeah. Because I need to multiply this thing by kilograms per gram, per 1,000 grams. Yeah, and I need to multiply by centimeters cubed per meter cubed, which would be like 100 times 100 times 100. Okay. Yep. We're on the money now. But we came up here so we could do rho SI is equal to those are tiny values. Now you know why we don't work in these values. We work in make sure I'm not doing something really wrong. Yeah, everything's looking good, I think. Let's just export this thing. See if I can remember how to like export something in Python. just make a list of the values and push them to a CSV file, and then we can mess with the data from there. dgx, dy, dgy, dz, dg, x, dz. Ugh. This has got to be like the slowest way to write something, right? Whatever. Everything I do is slow. Let's just call it like something super descriptive, like data. Sorry. That's like the worst name for a file. With open data, this file. Line and lines. How do you just write a line of data? Man. Oh, what we could do is we could I think this might have to be a tuple. Ugh. What I can do is this. Yeah. So that will produce a string of these things. Hopefully they'll just get like implicitly converted. Or maybe Python will do us a solid. How much do you bet this isn't going to work? Dang it. Okay. We're going to map the string function over the line. I wonder if you can just pass a map in between. Let's actually see that. Yeah, you can. Let's check data. Okay. It looks right. Okay, but nothing's in etvosh yet. Okay. Oh. Let's go back here. I think the number's like that. Let's go back to Google. CGS, SI base units. Times 10 to the negative 9. Jeez. So I messed up my units before, so let's again think critically. I think I have to multiply by 10 to the 9th to move SI to, yeah, okay. This is the line. Let's pull this back up too. Okay. I think let's just write it like that too, just to be like, just like the freaking Wikipedia. Always trust Wikipedia. Sorry. And how do I do this in a way that's not like horribly painful? 4 element in the element. Are tuples immutable? Let's try it. We're going to go from index 0, 1, 2, 3, 4, 5, 6, 7. I don't even know how to subscript anything anymore. this crash? Yep, it's immutable. So we just turned it into a list. Who cares? Watch that. Okay. Did that work? The values look the same to me. Yeah, like e to the negative 16th. Why didn't that work? I thought they would have been like way bigger. Ed Bosch. I cited Ed Bosch. Oh, because I'm not printing those new values. Let's actually check the data file. Yeah, now I'm at 10 to the negative 7. That's still egregiously small. Did I, like, do something wrong with my units? I've been known to do that. Oh, I defined that thing twice. Guys, this is bad. Okay, now they're like not ultra small. Okay, so I think we're done coding now. Let's just actually go look at these fields. Sorry, we're in the year 2025 and software still takes like a whole minute to open. I have no idea why. In my research, I'm working on some reduction to pull stuff, so that's why you see that there. I think I need to add a limited text layer. Hopefully I don't reveal sensitive documents. I'm trying to find my where in the world I stored that then. Where in the file system were we? I thought I called it like temporary. Yeah. This is a CSV file. Does not have field names. Well, I filled this field too. I need no coordinate system. Like, how can I get rid of the coordinate system? How do you get rid of the coordinate system in this? Okay. I could just like ignore the coordinate system. That's a bad idea though. There's got to be a way to do this correctly. QGIS arbitrary. Alternatively, we could just find points like in Colorado. The world is flat. Click on a new and click no projection in the CRS tab of properties. No CRS. Apply. Okay. Okay, now we're in some arbitrary coordinate system with our data. And here are all our fields. Let's just see whether, like, I don't know, we can give these better names or not. Oops. given these better names when I imported it. Okay, we're not going to give them better names. We're just going to plot these things. So I think we do this in properties, symbology, graduated x. I think this one was easy. So the second vertical derivative over cube should be like just down, and it should be down right over the top of the cube. Let's pick a. Okay, I'll pick a rainbow color map. Equal count, equal interval. I always forget what all these things mean. Let's do 32 classes. Yeah. So this is telling us that the lowest values are like right over the top of the cube. And does that make sense? Does it make sense for the vertical field to be negative, or should we make it positive? This is sort of a convention of sign, whether you want to be in the world of GIS and have Z be positive up, or whether you want to be in the geophysics world and have Z be positive down. Either way, the sign is sort of not important, but people like to put the pink areas over the anomalies. I don't know why, but we can do that too. I think we can like invert the thing somehow. Where's my invert? Maybe I can't invert the colors. That's ridiculous. Oh well, whatever. So this is a perfectly acceptable grid. Let's check the other fields. Let's check XX. Damn. Oh, I need to reclassify. Sorry. Say that's not good. That looks about right. Things are varying east to west, and in GIS, X is always east to west. Okay, sometimes in geophysics you'll see X is north. This is the same issue I was talking about earlier with the Z being positive and up in GIS and Z being positive down in geophysics. To make a right-hand coordinate system, the GIS people put X positive east, Y positive north, Z positive up. But the geophysics people do the opposite. They do Y positive north, X positive, X positive north, Y positive east, and Z positive down. They're just trying to make right-handed coordinate systems, and because of that you'll get sign errors if you're not careful. But that looks right for XX. Let's check YY. I think that was field 4. Click. Yeah. See, these things, they look like mirrors of each other if you're let me do this quickly just so you can see it. XX and YY kind of look like the same field, but just rotated. Kind of interesting, these symmetries that appear. Okay, but let's check XY now. XY was field 6. Classify again. Sweet. This is just what XY looks like, what we expect it to look like. Reclassify. Sorry, those, whenever the values disappear, that scares me. So the seventh field, what was the seventh field again? This is why you should name things better than me. Here's field 3, 4, 5, 6, 7 is YZ. So the change of the Z component of the gravity data in the Y direction. Does that make sense? So Y changes vertically. Does this make sense? Yeah, because if we take a horizontal derivative of a vertical gravity field, we would expect to see changes in the direction of the gradient. Okay, one more check. That was YZ. This is XZ. This actually should have some symmetry as well. So remember the shape of this field. Ah, yes. So it looks like the same thing, but just rotated. Okay, I think we're done here. I'm not really gonna like plot these up and make them look pretty. We could turn them into rasters. I mean, if we really wanted to make them look pretty. Let's see if we can do that. No, maybe it's not worth it. We'd have to grid it. Do we want to do that? How long have we been going? I don't know how long we've been going, but let's just cut this thing off. I mean, we got an answer, right? It's good enough. It's good enough to pass this class.